Alright, what's going on, guys? Your everyday math tutor here, and in this video I wanted to go over derivatives of polynomials and exponential functions. So this is going to be a bit of a long video here. We're just going to go over probably a few examples using some of the rules. We're going to go over just about 3 rules. One of them is the power rule for polynomials. The other one would be the constant multiple rule, and the last one that we're going to learn is the sum and difference rules for polynomials. And then we're going to go into the exponential derivative. So first, let's go ahead and go over our first rule that we are going to be going over, and that is called the power rule. All right, so here's the power rule, and it states that if n, if this could write, there we go, if n is any real number, then we have d over dx, parentheses x to the power of n, and that is equal to n times x to the power of n minus 1. So that is the general version of the power rule. So let's go ahead and take a look at some examples using the power rule. So the first example we have is the derivative of x squared. So our exponent is n equals to 2. So we'll have 2 besides the x, 2 times x, again, the variable. And then our variable, or our exponent, was 2, and we're going to have to subtract 1 from it. So 2 times x, and 2 minus 1 is just 1, but we don't write 1. We're just going to write 2x. So the derivative of d over dx, or the derivative of x squared, is 2x. Let's take a look at another example here. We have the derivative of x cubed. So n is equal to 3. So we're going to have 3 times x, 3 minus 1. That's going to equal to 3 times x squared. And this is the derivative of x cubed. And now let's do one more simple example. Let's say we have d over dx of x to the 4th power. So the derivative of x to the 4th would be 4 times x to the power of 4 minus 1, which is 4 times x to the power of 3. So I think we get what the point is. The exponent is going to be subtracted by 1 in this case. All right, so now let's take a look at another example here. So we have f of x is equal to 1 over x squared. Now don't freak out. You might be wondering, does the power rule still work for this type of fraction or this type of function? And the answer is yes, it does. We could rewrite this function as x to the power of negative 2. So that is how we can rewrite this function, and n now becomes negative 2. And so now what we need to do is take the derivative of that function, which is now x to the negative 2, and n being negative 2, which we already wrote down here. We would multiply it by x, and then we're going to be subtracting from the negative 2. We have negative 2 minus 1. So that is negative 2 times x, and negative 2 minus 1 is just negative 3. And this is the derivative of x to the power negative 2, but it's also the derivative of 1 over x squared. Now we have another example, and let's use the power rule to try and find the derivative of this equation here. So all we need to do is rewrite this to where we would have a rational exponent. And we know that the index of this radical symbol here is 3. And we know that that goes in the denominator. So what we would have is actually y equals to x to the power of 2/3. That is how we can rewrite this radical symbol or radical equation to have a fraction as an exponent. Okay, so now we can take the derivative, d over dx. Some of you guys might have dy dx, or some of you guys might have delta y over delta x, same thing. We're just taking the derivative of this function in particular. So now we have n to equal 2/3, so we can multiply 2/3 times x to the power of 2/3 minus 1. And we'll do the math over here. For 2/3 minus 1, we need to have the same denominator. This is 2 minus 3, which is negative 1/3. So our derivative is 2/3 times x to the power of negative 1/3. All right, so now let's take a look at the constant multiple rule. And what that says is that if c is a constant and f is a differentiable function, then d over dx, brackets c times fx, closed brackets, is equal to c times the derivative of f of x. So essentially what happened here is that we can factor out the coefficient of that polynomial. Let's take a look at an example where we use the constant multiple rule to find the derivative of a polynomial. Here we have the derivative of 3 times x to the power of 4. What we could do is factor out the 3 and then take the derivative of x to the power of 4. And we know how to do that using the power rule. So we're going to have 3 times 4x and then 4 minus 1. So that is just 3 times 4x to the third power. And then we multiply the 3 back with the polynomial here. And we're going to get 12x cubed as our derivative of 3x to the fourth power. All right, so here now I've written on the right of this example another example. We have the derivative of negative x. What is the coefficient here? Well, the coefficient is actually negative 1. So let me rewrite that so we could see it a little better. We have negative 1, this could erase, negative 1 times x. So we can factor out that negative 1 and then just take the derivative of x. And the derivative of a single variable with a degree of 1 is just going to be 1. So we have negative 1 times 1, which is equal to negative 1. So negative 1 is the derivative of negative x. And that, ladies and gentlemen, is the constant multiple rule. All right, so now let's take a look at the sum and difference rules. Essentially what that means is we'll take a look at the first one over here. That is the derivative brackets of f of x plus g of x, close brackets, is equal to the derivative of f of x plus the derivative of g of x. So essentially what went on here was we just distributed the derivative to each of the terms, and we will take the derivative of each individual term. And the same goes with the subtraction. Very simple. All we're doing is taking the derivative of each term in the polynomial. So now let's take a look at an example that uses the sum and difference rules plus an additional rule, which is the constant multiple rule. Okay, so here all we need to do is, and I know I get it, we don't have to do this all the time, but this is just for us to practice and see what, this means to have a derivative outside the parentheses and a long polynomial like this. All we're doing again is taking the derivative of each of the terms inside the parentheses. If you don't want, you don't have to, but it's always good practice to write this down. So the first derivative is the derivative, and again, we're just distributing. Essentially, we're using the distributive property to distribute the derivative to every term here. So the first one is the derivative of x to the power of 7. Then we have 2x to the fifth. But I know that using the constant multiple rule, I can factor out that 2 and then take the derivative of just the variable with its exponent. So that is x to the fifth power. Then I have 8 that I can factor out and then take the derivative of x squared. I can then take out the 6 and take the derivative of the single variable x here, and then take the derivative of just the number 3. So now I can take the derivative of every single term here. And the derivative of the first term, x to the 7th power, is just 7x x to the 6th. And then we have plus 2. And then the derivative of x to the 5th is x, or 5 times x to the 4th. Again, we're just subtracting the exponent here by 1. And then we have 8. And the derivative of x squared is just 2x. Then we have plus, and the derivative of this term here of a single variable with a degree of 1 is just going to be 1. So we have 6 times 1. And then the derivative of a number, the derivative of a number is 0. So we're going to write minus 0 just so you guys can see it. And now let's simplify. So 7x to the 6th stays the same. Then we have 10x to the 4th. Then we have 16x, because 8 times 2 is x, or 8 times 2 is 16. So we have 16x, and then we have plus 6. And this is the derivative of the function above. So what we used was the constant multiple rule, and we used both the sum rule and difference rule. All right, so what we have here now is the derivative of the natural exponential function. So pretty plainly, some books just have it as the derivative of e to the x, which is just equal to e to the x. Now, this one's a bit too plain. It may be a little bit deceiving, because what would happen if, let's say, we have, well, let's start off with an easy one. Let's say we had the derivative of 2e to the x. Now, of course, we can use the constant multiple rule to factor out the 2 and then take the derivative of e to the x. So we're going to end up with 2e to the x. So, hey, it looks like we end up with the same function. But what happens if we have something other than x as the exponent? Let's say we had the task of taking the derivative of 2e to the power of x squared. Well, now what? Is that equal to 2 ex squared as well? Well, it's not. So that's why I don't really like to use this rule, because sometimes we are given a different exponent other than x. So the rule that I want you guys to really copy down is the following. Even though this rule works, it's too general. So let's write a new rule. So let's say d over dx, or the derivative of e to the power of f of x, is equal to, now we can take the derivative of f of x. So we'll have the derivative of f of x times e to the x, or we should say e to the f of x, the original function. So now if we had that example that I have written down as 2e to the power of x squared, my f of x is actually x squared. So now if I take the derivative of x squared, I can multiply it by the original function here, which was just, actually it wasn't e, it was 2e to the power of x squared. Now all I need to do is take the derivative of x squared, which is 2x. So I have 2x times 2 times e to the power of x squared. And this is my derivative. So that is why I like to write this part here as my rule for the derivative of the natural exponential function. A lot to say, but bear with me. We're going to do some examples, and we'll see, hopefully, that we get used to using the derivative of the natural exponential function. All right, let's say we had the function f of x is equal to 3 times e to the power of x cubed plus 9. All right, so using the constant multiple rule, I can factor out that 3 and then take the derivative of e to the power of x cubed plus 9. So as the rule that I have written down, we need to take the derivative of the exponent here. So we're going to have 3 times the derivative of x cubed plus 9. And then just multiply by the original function, or at least without the 3, because we've already factored out that 3. So we have e to the power of x cubed plus 9. All right, so all we need to do is take the derivative of this. The only math we really need to do right now, at least the most difficult part, is just taking the derivative. The derivative of x cubed plus 9 is going to be just 3x squared. And then, of course, the derivative of 9, we could use the sum rule, but we know that the derivative of any number, just a number, is going to be 0. So we're left with 3x squared here. And then we multiply by e to the power of x cubed plus 9. Now you can multiply the 3's here, and we get 9x squared times e to the power of x cubed plus 9 to be our final answer here. So hopefully it makes a little sense. Maybe we need one more example. So let's go a little bit easier here. And we're going to try to keep this example on the left just so you guys could kind of go back and compare these two examples here. So let's say we have f of x is equal to, let me just make one up here, 2 times e to the power of x squared. Let's make it easy for us here. All right, so the first rule, again, it's always kind of good to write down what rules you're using. And I tell my students this all the time, even though I don't teach calculus, I teach 7th grade math. I still tell them to write the properties they're using, just so they could remember their vocabulary for math. So here we would be using the constant multiple. We're not going to write it, but hopefully you guys do. I'm not going to write it because I barely have space here. But we'll use the constant multiple rule to factor out that 2 here. And then we'll take the derivative of e to the power of x squared. So all we need to do is take the derivative really of the x squared. So we'll do d over dx of x squared and then multiplied by just the exponent to the power, or e to the power of x squared here. Again, remember, for when we take the derivative of an exponential or natural exponential function, we're really just taking the derivative of its exponent. So the derivative of x squared is 2x, and we would rewrite this as e to the power of x squared, and then we can multiply the 2's here as 4x. 2 times 2 is 4, and then we bring back that x. So we have 4x times e to the power of x squared, and this is our derivative of 2 times e to the power of x squared. That, ladies and gentlemen, was a really small lesson on the power rule, the constant multiple, the sum and difference rule, and the exponential function rule for derivatives. Hopefully you guys enjoyed the video. Hopefully you guys got a little bit of more insight here on how to do these problems. If you did, please leave this video a like, subscribe to my channel, hit that notification bell button down below to be notified when the next video is up, and I'll see you guys in the next one.